video, we shall begin to examine the concept of standardized data values, otherwise known as z-scores. You see, z-scores are simply a derivative of the distribution of a random variable x. What does that mean? If your x follows a normal distribution, from what we have discussed, it will have a mean value and to also have a standard deviation value that measures the average spread away from the mean. Now you see each of the values on the horizontal line here, if we take each of those values and we decide that each value we subtract the overall mean and divide by the standard deviation, then what you have are new values that can also form a similar distribution like this. In other words, if x follows a normal distribution, then the set of all values you get by subtracting the mean of all x values from x and dividing that result by the standard deviation gives you a z random variable that also follows the parent distribution, which means it follows a normal distribution. The only very interesting thing about it is that it will now be centered at 0 as a fixture. As long as that parent, that parent distribution has normal distribution, and the standard deviation will also be 1. So z-scores is a special kind of normal distribution where the mean is always 0 and the standard deviation is always 1. You see, before we get into the theoretical part, you want to note that in general, if you're dealing with sample data rather than population data, your z-scores can also be defined in terms of the sample mean and the sample standard deviation. So your x here are the raw scores, and your x bar is the sample mean in case you're not able to access the general population as we would in this case. And then you have the sample standard deviation, and then you have the z-score that results. Let's take an example of how z-scores can be used in a practical scenario. Two students, John and Ali, from different high schools, wanted to find out who had the highest GPA when compared to their relative school. You might notice immediately that John has a GPA of 2.85 and Ali has a GPA of 77. That tells us something. These two GPAs are not measured on the same scale. So how can we compare each of these students to each other just within the context of how each of them is doing in their relative schools? To do that, since the GPAs are not on the same scale, we can use the z-score of each of these values to bring them to the same scale, that is the z-score scale, and then it becomes comparable. Let us see how to do that. So we have that of John and we have Ali. And for John, what is the z-score for John? So for John, we're going to take the raw score for John minus the overall mean score in John's school all over the standard deviation in John's school. That'll be going to John, the raw GPA is 2.85. In John's school, the overall mean is 3.0 divided by the standard deviation 0.7, and we have negative 0.2143. Whereas in Ali's school, we're going to take Ali's GPA minus the overall average in Ali's school all over the standard deviation in Ali's school. So that will be equal to 77, the raw GPA, minus the mean, 80, divided by 10. That will give us negative 0.3. These are the z-scores for both students. Well, these two scores are pulled onto the same scale of z-scores. And so if I have 0 in the middle, negative 0.2143 is here, and negative 0.3 is somewhere here. It appears that this value, negative 0.2143, is closer to what? 0. And you might notice that as far as GPA is concerned, higher is better. And since higher is better, the person with a higher GPA is doing better. And that would be John in this case. So John has what? A higher what? Z-score. And since that's what we desire in this scenario, so he has what? The relatively higher GPA, which means he is performing better relative to others in the school as compared to Ali relative to others in Ali's school. All right. And we look at yet another example to illustrate that. The Vikings scored what? 773 runs and playing Division B for high school baseball. And in that division, the mean number of runs was 677.4 and standard deviation was 51.7 runs. So for the Vikings, we have that. We have the mean is for the Vikings, they had 773 runs. That was their raw score. And the average, the overall average is 677.4. And the standard deviation is 51.7. So as it stands then, the z-score for Vikings will be raw value minus the mean divided by the standard deviation. That will be 773 runs minus the overall average in that division, which is 677.4 divided by 51.7. That gives us 1.8491 for the z-score for Vikings. Then you have the z-score for the Houghton Lake Bobcats. So for the Bobcats, they scored what? 775 runs. They play in Division B, not in the same division as the Vikings. So different scales of difficulty. So it becomes difficult to compare the number of runs directly across different divisions. Okay, and the mean number of runs for the Bobcats was 640.0, and the standard deviation in Division C rather is 55.9, and the mean average in the average number of runs in Division C is 640, and the z-score for the Bobcats then will be x minus mu all over the standard deviation. That will be 775 minus 640 divided by 55.9. That will be equal to 2.4150. On the same z-score scale, I have 0, I have 1.8491, and I have 2.4150. In context, the more the number of runs, the better. So that means the person who has the higher z-score is doing better, is having a relatively better run producing season. And in this case, that would be the Houghton Lake Bobcats. They are having a relatively better run producing season since their z-score is the higher of the two. Take note that I've been emphasizing that their z-score is higher, and that is because of the context. Let's take a flip scenario. One year, the fastest male runner ran the Boston Marathon in 1:27.95 minutes. Among all men in the race, the mean finish time was 227 minutes with a standard deviation of 47 minutes. So let's look at in the category of males. So there was the fastest male runner. The raw number of minutes was 1:27.95 minutes. And in that category of men, the mean the average was 227, and the standard deviation was 47 minutes. So the z-score for this fastest meal will be equal to 1 will be x. Let's rewrite that formula. I'd like to x minus the mean divided by the standard deviation, how far the raw value is from the mean, scaled by what? The standard deviation. And that gives us negative 2.1074. Then for the fastest what female runner, let's see. That same year, the fastest male runner ran the Boston Marathon in 143.52 minutes. Among all women in the race, the mean for women was 248 minutes and a standard deviation of 43 minutes. Who did better in relation to the agenda? Well, to get the z-score for the fastest female runner, we have x minus mu all over the standard deviation. That will be 143.52 minus 248 divided by 43. So uh, that will be negative 2.4298. Now I can compare the two z-scores together. So let's see. Z-scores, I have my 0, and I have negative 2.1074 and negative 2.4298. It becomes obvious that the bigger number here is this, and this is the smaller number. But in the context of this problem, we're talking about run time, time taken to run a marathon. Do we want, is it desirable to have a higher number or a smaller number? Yes, we would prefer if the time is run in small, if the finishing time was shorter. So in this case, what is preferred is the smaller run time, and that pertains to the fastest what? Female runner. So in this case, who did better in relation to gender? That would definitely be the fastest what? Female runner. Based on what we have learned about the z normal random variable, so we want to emphasize that if x is a normally distributed random variable, originally with its mean and standard deviation, if you converted your x to z by subtracting the mean divided by the standard deviation, the resulting z will also have a normal distribution. However, the mean will now be 0 and the standard deviation will always be 1 for a standard normal random variable. So here's an example. For a standardized normal distribution, which means it has already been standardized, and that means this terminology, standardized, means take the mean to be 0 and the standard deviation is 1. We have to calculate the following probabilities. I'm going to split my screen at this point. So let me do this. And we have that piece. Okay. So let us see. In this case, if I want to find the probability that z is probability that z is less than 1.7, then I'll need to take the standard normal distribution, whose what mean is always 0 and the standard deviation is always 1. This is true for any standard normal random variable. And we want 1.7, so I will locate 1.7, and I'm interested strictly in the probability to the left of 1.7. That'll be this whole area. And I'll go back to, I'm going to close out of this, go to Stats, go to Calculators, go to Normal Distribution. Take note that this always defaults to the standard normal distribution, 0 and 1. And in this case, we're interested in the area below 1.7. So I want less than or equal to 1.7. And I will compute that. So that will be equal to 0.9554. Then next, I want to find probability of z less than or equal to 1.7. It's a good time to remind us that for measured or continuous random variables, whether you put equal to or you don't put equal to, you will get exactly the same value. So this is also equal to 0.9554 when we're dealing with measured or continuous random variables. Then let's see the case of greater than or equal to 1.7. That's all a matter of changing this to greater than or equal to 1.7 and compute. And I have 0. I have 0.0446. Then similarly again, I have greater than or equal to negative 2.05, and that would be equal to 0.9798. Then I would like to illustrate what this looks graphically. So this is again, since we're dealing with the z random variable, the standard normal, the mean is 0, and then the standard deviation is 1. And I'm interested in the value negative 2.05, and I want to look at the area to the right. So that will be the area to the right of negative 2.05 here. And that the size of that area is this probability. Then next we have what? Between two values. Sure, we click on between. Keep what? The parameters of the standard normal random variable are 0 and 1. And we're interested in negative 1.19 and positive 1.15. And compute, you have equals 0.7579. Similarly, a similar argument can be made for question F, in which case I'm just only changing this to negative 0 and positive 1.04 and compute. In this case, we have 0.4262. Okay. Very similar example here in question G. All a matter of changing this back to negative 1, and then this is 1.19, and what would that be? So that is between those two values, and we have 0.7659. We finally, on the normal distribution, take an application problem. So to do that, let me zoom in back in here. The Coca-Cola bottling plant's product line includes 12-ounce cans of Coke products. The cans are filled by an automated filling process that can be adjusted to any mean fill volume. Take note of that. And that fills cans according to a normal distribution. However, not all cans will contain the same volume due to variation in the filling process. So we have a variable here. Historical records show that regardless of what the mean is set at, the standard deviation in fill will be 0.035 ounces. Operations managers at the plant know that if they put too much Coke in a can, the company loses money. If too little is put in the can, customers are shortchanged, and the State Department of Weights and Measures may fine the company. So A. Suppose the industry standards for fill volume call for each 12-ounce can to contain between 11.98 and 12.02 ounces. Assuming that the manager sets the mean fill volume at 12 ounces for this part of this question, what is the probability that the can will contain volume of Coke product that falls in the desired range? Well, the desired range is between 11.98 and 12.02 ounces according to industry standard. So in this case, our X is what is the fuel volume? Is the fuel volume for each what? Each 12-ounce can of Coke product, and it will vary. And if it is varying according to a normal distribution that was indicated at this point. That the fuel volume fuels according to a normal distribution. So our X in this case forms a normal distribution. And based on that, let us see. We have the mean. The mean fuel volume for this part of the question is provided here, that the manager set it at 12 ounces. And then we were also told earlier, we were also told that the standard deviation is 0.035 ounces. And our interest is what is required. What is required is to find the probability that a can will contain a volume that falls within the desired range. So X, the volume, falls between this range, 11.98 and 12.02 ounces. So I'm going to locate those values, and I have 12.02 ounces, and I'm interested in the probability sandwiched between those two values. So what will that be? I'll go to StatCrunch. Let me do that. And I want between. I'm going to key in the parameters of the distribution, which is 12 and 0.035. And I want the amount of probability between 11.98 and 12.02 and compute. So this is equal to 0.4323. So what is the interpretation of this? About 43.23% of what? Of cans fall in the desired range. Fall in the desired range. This is definitely a cause for concern. This is under what? 50%. Is meeting what the industry standards say should be for the fuel volume. How can we adjust this process? How can we apply statistics to make an informed decision here? Well, we might need to reset or recalibrate the automated filling process. Well, we can adjust the mean fuel volume to a different volume, to a different mean, to see if it results in a change in that percentage. So question B builds on that. Assume that the manager is focused on an upcoming audit by the Department of Weights and Measures. She knows the process is to select one Coke can at random, and if it contains less than 11.97 ounces, the company will be reprimanded and potentially fined. Assuming that the manager wants at most a 5% chance of this happening, at what level should she set the mean fuel level? Comment on the ramifications of this step, assuming that the company fills tens of thousands of Coke of cans each week. Okay? In particular, our initial focus is what value should the mean be at. Okay? To do that, whenever we want to find an unknown parameter of the normal distribution, we should note that our interest here, I'm going to split this into two, is to note that what is required is to find the mean such that the probability that the amount that will be in a particular can, it contains less than 11.97 is at most 5%. So that is the worst case scenario, is at most 5%. So what value should we set mu at so that this is realized as a goal? Well, I can sketch the normal distribution for x, and in this case, I do not know this time what the mean is. Of course, we've been told that regardless of what the mean is going to be set at, the standard deviation will always be 0.035 ounces. So standard deviation is fixed at this value, 0.035 ounces. Okay, so what we want to find is the mean, such that this is realized. Take note that 11.98, is it to the right or to the left of this unknown mean? If we set it to the right, let's say 11.98 is here, well, the area below it, because you want less than, that'll be all of this area. That is more than 50% of the total area under the curve. Well, that would not align with our objective, which is to set it at most at 50%. So we know 11.98 is not to the right of that mean. We know that it has to be to the left of the unknown mean. Well, so if we want at most the area here to be 5%, according to this question, the area to the left of 11.97, excuse me, I meant to write 11.97. Yes. The area to the left is as much 5%, and we need to find the mean. To find the mean, what we do is we translate this distribution, we transform it to a standard normal distribution. So instead of x, we now have z. The mean is always 0, the standard deviation is always 1, and we want to find a particular z value. Z is always x minus the mean divided by the standard deviation. So the mean we do not know, but the standard deviation we know to be equal to 0.035 according to the question. And what is the z-score? Well, what is your x-score? Our x-score is 11.97. So I'm going to change my x here to 11.97. And the z-score, what is the z-score here that corresponds to 11.97? That should come here. To find that, that means I can go to the standard normal distribution. So let me go to the standard normal distribution. I'm going to change this to 0. And the standard deviation is 1. And I want the standard case. And I want to find a value of z so that the area to the left is what? 5%. So to the area to the left of an unknown z value captures what? The bottom what? 5%. So compute. This is negative 1.645 approximately. So I'm going to put that here, negative 1.645. Good. And my goal is to use this equation, which I'll pull up here, to solve for the only unknown, which is my mean. So let's see how that is done. So you have negative 1.645 equals 11.97 minus the mean divided by 0.035. So as it stands, we're going to cross multiply in this case to solve. So I have 11.97 minus the mean equals negative 1.645 multiplied by 0.035. So 11.97 minus the mean is negative 0.057575, or 11.75 plus 0.07575 is equal to the positive mean. So that our mean is 12.027575. This is what they should set the mean to so that there is at most a 5% chance that a randomly selected can will contain less than what? 11.7 ounces. This is the desirable one. That is the first ramification of the step. Another ramification of this step is that if they fill tens of thousands of 12-ounce cans of Coke products weekly, the extra Coke products will usually affect the financial bottom line of the company. So I recommend finding a working strategy to reduce the standard deviation to ensure a more consistent fuel volume per can of Coke products. This is a wonderful application of how we can use statistical methods to solve a real life problem in a production process.